So this paper is in Nagoya Journal. I think around 1990, around 2000, I don't know. So I will eventually get around to explaining what this has got to do with Bombieri's embedding theorems for canonical surfaces. But let me kind of set the scene in a slightly different way. I want to take a curve C, and I have in mind a curve which is singular or possibly reducible or not reduced. So fairly complicated curve, and I want to assume it's, but I do want to assume it's a Gorenstein. So I started explaining this at the end of last time, and I'll say it again in a few words more recently. So plus some conditions. So the conditions especially is something called K connectedness, which I have to redefine. So this is not the same definition as before. And then I want the same ampleness. Properties as a non-singular curve. So by this I mean if I've got H, a Cartier divisor, and the degree of H is greater than or equal to 2G plus 1, which is, of course, the degree of Kc plus 3, then it's very ample. H is very ample. Right, and degree of H is 2G plus 2. Well, it's basically the same condition, the same conclusion, except for one case, except if I've got something like Kc plus P plus Q. Right, so if you take the linear system, if I take a non-singular curve and I take Kc plus P plus Q, then all the sections of these guys, if the section vanishes at P, if it doesn't take up its full pole at P, then also it must also vanish at Q. And so these 2 points are automatically going to be identified by the map corresponding to this. And then also this is to do with general divisors, but also Kc is very ample, except hyperelliptic. Right. So I'll come back. I'll explain how to extend these results to an arbitrary curve C, which is Gorenstein, and which is K two connected or three connected in the sense that I'm going to make precise. And so in the second half of the talk, there'll be I'll show how to use this to get Bombieri's theorems. And in fact, you know, quite a strong form and quite a neat proof without any extra assumptions. So it's this is quite a nice application. Okay, so I've got a curve C, and it's, you know, probably non-reduced. So think, you know, singular, possibly non-reduced. So all the curves I've spoken about so far in this course are always curves on a non-singular surface, and that's and you know, that's a kind of concrete assumption. I'm trying to get away from that. So I'm just going to assume that, so it's projective, of course, and then I want C to be Gorenstein. So let me So there's this kind of little preliminary thing I should say. It's Cohen-Macaulay, right? And this means if this happens, if and only if OC has no sections with zero-dimensional support. So of course, when I say see, I want a curve. I want it. It's purely one-dimensional, right? So I'm allowed to have sort of various, you know, fairly complicated, non-reduced things. But well, the thing I'm not allowed to have is something like this, where, so you know, for example, if I write down, you know, x to the fourth equals 0 and x cubed y equals 0. Then sitting inside there is this guy x cubed, which is not 0, but xy times the x cubed equals 0. Right? So in this case, there's this little sort of shadowy nilpotent function that lives at this point, and it dies immediately you go away from the point. Right? So this is not allowed. So, you know, if you want to, you can, if you do commutative algebra, you can say the associated points of the sheaf OC, and this are all one-dimensional. Right? So anyway, we're going to see. This is a reasonable condition. We could always just kill any of these sections. Right? So Gorenstein. Anyway, you know, I have to say the definition. So this is if and only if, for every point, for all p in C, there exists an element S in OC of OCP, which is a non-zero divisor. Right. So at every point of the curve, it means I can choose some element S. And setting S equals 0 is a non-zero divisor. It's I'm genuinely cutting the curve by a non-zero element and cutting it down to 0 dimensions. Okay, so I mean, if you know the commutative algebra, you can easily get this. But in any case, if you're worried about this, then you don't worry. Just assume it. So Gorenstein means the above condition, Cohen-Macaulay, plus omega c is isomorphic to, locally isomorphic to OC, and this is the same as saying that omega c is OC of Kc, where Kc is a Cartier divisor. Right, so Cartier divisor is defined somewhere in Hartshorne chapter 2, and so what it means is this. What it means is I can write down the Kc as a combination, as a multiple of elements here that are not non-zero divisors. Okay, so if you're seeing the Grothendieck dualizing sheaf omega c from the first principles, so you know, who is this guy omega c? And so you know, one way of saying this is, well, you all know Hartshorne chapter 3, so omega c is defined as x n minus 1. 1 is the dimension of OC into omega of Pn. Right? And so, you know, I mean, this is sort of nonsense. It doesn't really tell you anything. But it does say that in principle, somewhere in there, if you know everything there is to know about sheaves on projective space, and, you know, this is just some kind of derived functor business, then eventually you can figure out what the definition of omega c is. Okay, so that's a sort of bad definition. So better definition, omega c is uniquely determined by the property so H1 of omega c is one-dimensional, so this is mapping isomorphically to K. This is the ground field. Right? And I just choose an equality here. Right? And everything, several of the steps I make later, depend on making this choice. Uniquely but depend on this, and H1 of F dual is equal to Hom F omega c. Okay, for all, this is Hom OC, where for all F coherent on C. Okay, so what this means is, for every linear form, H1 of F maps to K, there exists a unique homomorphism.
This is not the sheaf form, the group form. You write the form as a sheaf.
Yes.
It's the group.
It's a Hom as a sheaf of OC modules.
But the group,
it's a group. The left-hand side and the right-hand side are both groups. You want me to write straight Hom? Yes, yeah, of course. Of course. This is, I'm working in the category of coherent sheaves with homomorphisms between coherent sheaves, and the homomorphisms are OC linear.
yes, but this is an equality of
It's a
groups.
group. It's a group, yes. Okay? So this statement here I'm making is that every time I've got a linear form, then there exists a unique homomorphism F to omega c, such that F, when I do H1 of F to H1 of omega c, to this chosen isomorphism here, my lambda is this. So every time I've got a linear form here, let's call it lambda, then lambda is induced from this. Right, so another way of saying this, so omega c represents the functor F maps to H1 of F dual. Okay, so I mean, this is sort of strange rigmarole, and it's sort of not at all clear why this is useful. But anyway, you have to go through this machine. Well, the thing I'm telling you here is a lot simpler than, Hartshorne residues and duality. Yes, and so if this were not 1 but n, you could write the same n, and you get the same definition, same characterization of the pre-dualizing sheaf. Okay, so the fact that this omega c exists, well, one way of doing it is saying, well, we all know everything about X on projective space, homological algebra. Okay, so I'm going to take this as a, I'm just going to assume this stuff from now on. I mean, I learnt this myself a very, very long time ago, and I don't know how to explain it any differently. Okay, so suppose I've got C, and I suppose I've got B, a curve inside C. Right. So maybe C is, it might happen that C is 2A plus B. Oh, sorry. It might happen that C is 3 gamma 1 plus gamma 2, and B is gamma 1 plus gamma 2, for example. So you know, I'm especially interested. I'm especially interested in excluding the cases where these guys have common factors. So I have to deal with this. I can't just deal with the right. And so then there's an ideal of B inside O of C, and so then an OB module, a sheaf of OB modules. I'm always coherent. And a coherent sheaf of OB modules is the same thing as an OC module killed by IB. Okay, and now I'm going to tell you something which is really magic. So if F is any OB module, and F to omega C is a homomorphism, of OC modules, then this F maps in a canonical way to hom OB into omega C, contained in there. Right, and this guy here is omega C, omega B. Okay, so you know, on the one hand, this is very useful and very subtle. On the other hand, it's completely trivial. Right? So this guy here is an OB module. So he's killed by IB. Right? So if I take an element in F, a local section of F, and I map him somewhere to a local section of omega C, then he's got to map to an element which is also killed by IB. Right? And that's the same thing as a homomorphism from OB into omega C. So this thing here is the same as the sheaf of local sections of omega C killed by IB. Okay, so why is that the same thing as omega B? Well, if I've got an element of H1 of F, H1 of BF, that's just the same thing as H1 of CF, right? Because the sheaf is, this F is a sheaf on C, and he happens to be spotted on B, right? But taking the H1 doesn't ask about the spot; it's just one and the same sheaf, right? And so this guy, this F, a section here. A linear form on either of these spaces is a homomorphism of F into omega C. So this is saying homomorphisms from F into omega C is one and the same thing as homomorphisms from F into omega B. And therefore, this, because the omega is the thing that represents functor, because of that, mumbo jumbo, because of this, complicated but trivial stuff I said there. This is okay. So in our paper, so this statement, the statement that hom OB OC omega C. So I write the omega OC here. So the shape of this is the same, is exactly the same shape here. There's this thing here, this curly X'd, which is just part of the hom functor. It's the hom functor extended out into some category of complexes, or some derived category, right? And then where's it homming from? Well, I'm talking about trying to establish something which is going to give me duality for sheaves on C, and so they're always OC modules, so if I've got a sheaf on C, in particular it's a sheaf on Pn, and so I can try to figure out his cohomology, his X, by Xing into this omega, and if I do that, then I'm sort of passing through various functors, and I'm ending up homing into this thing. Right. So this thing here is omega b, and one of the basic. So if I've got duality for a finite morphism, this is a very useful thing to know. So if I've got x to y finite and the same dimension, so this could be a covering, or it could be an inclusion of one in the other, or it could be lots of other things. But I'm just saying this is a finite map, and between things the equal dimension. Then there's an f there. Then there's f lower star of omega x is hom f lower star ox into omega y. Right? And basically the proof is just exactly the same as the proof I gave here. Right? If I've got a sheaf on x, I can think of him as a sheaf of OY modules. I can take f lower star of the sheaf and think of him as a sheaf of OYs. Right? And therefore, it's a sheaf it's a special, so f on x and lambda in h1 f dual, a linear form on h1f, then there's an f lower star of, I can think of the f lower star of f, this is a sheaf on y, with an OX module structure, right? But he's a sheaf on y, he's a coherent sheaf on y, and therefore his h1, therefore the h1 of f is the same thing as h1 of f lower star f, right, and so on. So therefore this is governed by homomorphisms from f lower star of f to omega y. So the lambda is given by applying the same arguments there. So you follow through the argument, and you'll find that the thing that represents homomorphisms from OX modules into omega, into this f lower star omega x, is the h1. I'm sorry, I didn't say that exactly right. So this sheaf f lower star x, f lower star omega x, this sheaf here represents the functor of linear form. F goes to linear forms on f for functors on x. Anyway, let me just leave it like this. So in particular, if your x to y is one of these standard double coverings or something that you find in constructions of algebraic geometry, then if you know the f lower star ox and you know the omega of the image, then you get immediately the good structure there.
Right. The quantity between h1 is by Leray spectral sequence because the map is finite.
Yes. Well, it's the basic property of finite maps.
Yeah.
With finite maps, basically you shouldn't write the f lower star. The thing is to interpret this as a sheaf of OX modules, okay. Right? A sheaf of f lower star OX modules. And, so a sheaf on X, for a finite map, a sheaf here and a sheaf there is basically the same thing. It's just a matter of what algebra you're considering it over. And then, as you say, this equality of cohomologies, it's the basic property of finite maps. Finite maps in particular are affine.
Yeah, finite.
Okay, so now I want to tell you what two-connected is. So numerically two-connected. So C is, this is the definition, C is numerically K connected. If for all B in C, this is the thing you're not going to like, generically Gorenstein, so I want the B and not equal. Right, so the picture I have is this. I have some complicated non-reduced curve, and I have some curve sitting inside it, which probably shares some of its components and is not equal. Right, then what I want is that the degree of OB of KC, so that's the same thing as omega C restricted to B, minus the degree of omega B is greater than or equal to K. So you remember that if C is a curve on a non-singular surface, then I can, if I've got C contains B, this is the same thing as C equals A plus B with A and B both positive. Right? And then the condition here is, in this case, the condition would be I take B and I take his intersection number with K plus A plus B, so that's this thing. Right, and then I take the degree of omega B, and so that's B times K plus B. Right? And of course this is the same thing as AB. Okay, so in the particular case of a curve on the surface, then I haven't, the definition here is the same as the definition there. However, the subtle point is this, that here I've got C is A plus B, and so, you know, this situation here is completely symmetric between A and B. But here, this C could be, you know, some sort of fat, non-reduced curve, and the B could be something sitting inside it. You know, so for example, you know, it could be that C is something like this. You know, so some kind of fat infinitesimal thing, and the C could be something much, much thinner inside it, right? And so, you know, the A doesn't make any sense at all. The A, in this case, I'd have, you know, the ideal of B inside OC, but A doesn't, you know, can't be seen. Right? So this condition here is sort of symmetric between A and B. So here I'm saying, well, you know, in the general case, maybe, you know, maybe this C doesn't belong on any surface at all. Maybe it's completely, you know, completely general, non-reduced curve. Nevertheless, I'm assuming it's Gorenstein, and so I can take its canonical class and restrict that down to B. Right? And then, well, what am I going to use instead of this thing? Well, I'm just going to use the degree of omega B. So, you know, this is just a definition. The use of a definition is, you know, how are we going to prove this in cases? So I'll explain that in the second part. And how are we going to benefit from it? How are we going to make any use of it? Because you won't be able to guarantee that. So, you know, for example, I might have S, a surface, no, sorry, X, a surface with Duval singularities, and I might have C, so, you know, here's my X, here's my C, right? And so if C is a Cartier divisor, right, so Kx plus C restricted to C is, you know, omega C. Right, but if I take B inside C, maybe it's not Gorenstein. Not necessarily. So look, you know, the problem with lecturing this abstract stuff is that you don't actually see the example. So let me give an example. So here is the ordinary double point, ordinary node. Here is 4 lines on it, 4 generators, 4 generating lines. I've got 4 generating lines on there, then this is locally a complete intersection. So it's Gorenstein. Right, so if I've got 4 lines in space, 4 lines in space where the rule is any 3 of them are linearly independent, and the 4th one is then dependent on them. Right? So this is a cone over a projective frame of reference. This is Gorenstein. But if I take this, 3 lines in space, it is not Gorenstein. Okay. So you know, why is it that 3 lines in space is worse than 4 lines in space? Well, you know, maybe it's not worse. Maybe it's you know, we shouldn't apply prejudices. But anyway, it's just different. So so you know, when at some point I'll do some calculations of these, what the canonical class is for these, and we'll see in this case it's locally free, in this case it's not locally free, it needs 2 generators. Okay, so so C numerically 1 connected implies that H1, H0 of C is the constants. Because suppose I've got F in OC. Suppose I've got F in H0 OC. Right, and if F vanishes at some generic point of C. Okay, so you know, imagine that my C is like this, some complicated curve, then and assume that this H0 of C is at least 2-dimensional. Right? Then I could choose a point here, and I could say, right, I'm only going to look at the guys that are 0 at this point. And so this is if this were at least 2-dimensional, then that's still a 1-dimensional vector space. On the other hand, if I now restrict him to that curve, he's a function on a projective curve, connected projective curve, that's got at least 1, 0. And so therefore he vanishes along that curve. Right, then if I write F from multiplication by F, So it's F, I'm thinking of it as mapping omega C into F times omega C. Right, and then, so the support of F is a curve B in C and not equal to C. Right, so in other words, I arranged that that the annihilator of F inside OC is not 0. That was the point here. So you know, if the one I said was let's take the F and assume that the F vanishes along this curve. Right, so maybe he vanishes to some multiplicity along the curve, but he's not identically 0, so he doesn't vanish everywhere. Right, so if I take the set of guys that annihilate that F, then it contains at least so anyway, this defines B. But then I've got, but then F is a homomorphism, isn't that now, is a homomorphism from F takes OB into omega C, and therefore it factors through. It necessarily factors through hom OB of C equals omega B. Right, and so the thing I've got here is, here's my OC. I started off with an F with a map to, I'm sorry, here's my omega C. I started with some map to omega C, but actually it's mapping to omega B inside that. Right, it's first of all it's dividing out by the ideal of B, and then it's mapping to some omega B in there. And this omega B is generically generated by the image of F. Yes? But now this is contradiction. Right? Because I've got omega B, omega C restricted to B is mapping injectively to omega B. Right? But the degree of this one minus the degree of this one is positive. This is contradiction. Okay. So you know, it's a curious argument. So you know, like it's a curious argument. I'm supposing that I've got some non-trivial element here. So you know, if this group is at least two-dimensional, I can certainly find some element in there that vanishes on one component. Right? Now I consider the multiplication by F. So it's going from, you know, I could take this to be OC of KC. This is a locally free sheaf by assumption. So it's mapping its multiplication by this. It's mapping it into some sheaf of omega C. So there's a sheaf of ideals that kills the F. And that's the sheaf of ideals defining a curve B. Right? Then the map here, first of all, kills the annihilator of F, and then it maps generically injectively to something, and this something is necessarily omega B in omega C, where this B is generically Bernstein. Right, this is just by construction. This omega B here is generated at every general point by a single element, namely the image of this homomorphism. Okay? So that's how the argument's going to work. You can, you know, think about it. You can go back to the original paper and so on, but it's basically the same argument. Right. And then the second part is that C numerically 2 connected implies, so this should remind you of what you do when you do Riemann-Roch, when you do the first consequences of Riemann-Roch, implies either Kc is free or C is isomorphic to P1. So, you know, I explained how to do some of these things for curves on surfaces and so on. And here we're seeing the same arguments again, but just in this sort of very strange, very kind of arid technical language where you're not allowed to just use your common sense and blow up points to make the curve non-singular and so on, but you really have to get involved with these crazy scheme theoretical definitions. Okay, so how am I going to prove this? So, you know, I'm going to take x in C, and I'm going to look at the maximal ideal x times, let me write OC of Kc. Right, and so this is, of course, mapping to OC of Kc, mapping to, you know, whatever it is. Oh, let me write O little x of Kc. Right, so the assumption, the base point. So let's assume if there's a base point, if x is a base point. Right, it means that H naught here, OC of Kc, is mapping not surjectively. So let me write not surjective to H naught of this guy. So in other words, every section here belongs to the maximal ideal. Every section vanishes at the point P. Right? And then let's chase this along. This is H1 of the maximal ideal of x times OC of Kx. Kc mapping to H1 of OC of Kc. Right? So saying this map is not this map is not surjective is the same thing as saying this map here is not injective. Right? So, you know, the purpose of having these dualizing sheaves is to be able to dualize. And so, you know, what am I looking at? I'm going to say that, so the dual of this is, so H naught of OC is mapping to H naught, so is mapping to what's the dual of this? So let's go back. Let's be sort of pedantic about this. Think of this is H1 of something, right? And the definition of the dualizing sheaf is that this H1 is the same thing as HOM. Is the dual of HOM of OCKC into omega C. Okay, they're the same thing. So it's sort of. I'm just making pedantic definitions, so maps to HOM of MPX, MX times OC of Kc, omega C. Okay? And so this statement that this map is not injective is the same thing as not surjective. Okay, and you know, well, I'm going to repeat this argument 2 or 3 times. And you know, when I was doing the Bombieri-Ramanujan arguments in the previous times, there was basically the logic is exactly the same. We're finding some map not surjective, and we're chasing it around and so on. And then we're dualizing, and then we say that we know something about the kernel of the dualized map or something. Right? So what is this? So, in other words, there exists an S from mx, maximal ideal x, OC of kc, into omega c. And so, you know, this is, of course, omega c, which is linearly independent of the identity inclusion. Okay, so I mean, we know another map here. We already know a perfectly good map here, which is namely maximal ideal x times omega x is just contained in omega. Right? So it's linearly independent of this one. And so, you know, it's basically the same. I can now apply the same argument because I can now take one of those functions and make him vanish at any point. So I have two sections. I have 1 and S. Okay, and now I can forget that it's omega c and just write OC. So let me write. Let me choose. So if let me say S minus lambda times 1. Right? So this is a homomorphism from mx into OC. Sorry. Or, you know, it's the same thing as omega c into omega c, mx times omega c. I don't know which of them is going to be more convenient. So I have a 2-dimensional space of these sections. Right? This one has a tendency to be, you know, a generator everywhere, you know, an isomorphism everywhere, at every point. So for any point x in C, sorry, any point y in C, y not equal to x, I can choose lambda so that 1 s minus lambda times 1 is maps to the maximal ideal at y times OC. So now I've got this situation. So let's sort of think here. In other words, you know, I'm just taking tensor product down, twist down with Kc. So, you know, omega c is OC of Kc. So I can twist down by Kc. Okay, so having done this, I've got this map mx times OC maps to my times OC. Okay, so what can I do with this? Well, so you know, this is just this S. Let me call this S. Let me just call this S prime. So if S primed vanishes on any component, of C, we get a contradiction to two connected. I'll spell this out. Okay, if it doesn't, if S primed doesn't vanish, then what it says is mx times OC is isomorphic to my times OC. Isomorphic as sheaves of OC modules. Right? And this says, in particular, that this implies that every point of C is non-singular, and x is linearly equivalent to y. Right? So this guy here is a locally free sheaf outside x. Right? And that implies y is a different point from x, and so this guy here is, this implies that y is a Cartier divisor. And that implies that, you know, the only way that a reduced point can be a Cartier divisor if it's a non-singular curve. Okay? So we're winning something. When did I start? Oh yeah, okay. Okay, and so this implies P1. This implies C is isomorphic to P1. Okay, so let's spell this out. Let's spell out this argument, but it's basically the same as this. It's the same as this mapping down to a B. So let's justify this. So if write B, write IB for the annihilator of S primed. Okay, so I've got this map here. Now I'm going to go back to this. Now I'm going to go back to the omegas. So I've got this map mx times omega c maps to, this is the S primed, maps to omega c, and so this is mapping down to mx times OB of kc. Should have written that OC of kc. Right? So I'm just saying that the S primed is annihilated by something. So the support of this S primed is not the whole of C, it's some subcurve lying inside it. Right? And now, and so this is just dividing out by the annihilator, and then this maps there. But this has got to map to omega B inside there. Right? Just because I'm homing from an OB module into omega C. And so there's this automatic adjunction thing happening, which I think I've erased. If I'm homing from an OB module into omega C, I necessarily factor through omega B contained in there. Okay? And this is a contradiction. Because this says that so this says on the first place that this B is generically Gorenstein. So omega B is generically generated by one element. Right, so outside the extra special zeros of S prime, this omega B is generated by S prime. Right. On the other hand, you know, what have I got? I've got the degree of Kc restricted to B minus 1, and then this has got to be less than or equal to the degree of omega B. Right. And this contradicts. This is a contradiction. It contradicts two connected. So, you know, this category of curves is sort of basically a strange thing. You know, I'm not imposing any non-singularity restrictions on the curve C at all. I'm just assuming that there's a nicely defined line bundle called the canonical bundle. Right? And then you get out automatically that it satisfies these same properties as, you know, this is the basic property from Riemann-Roch on a curve. Either KC is the free linear system, so, otherwise either you get a free linear system, or you get, or you know, the alternative case is that C is actually a curve of genus 0 and that C is isomorphic to P1. So where do I go from this? So, you know, the have I got this written down somewhere neatly? So let me give this definition. So, you know, what would be, this is saying, this was the first step in Riemann-Roch. Right? If I've got a curve of genus greater than or equal to 2, then Kc is the free linear system. Because otherwise, you take a point off it, you take Kc minus P. If the dimension of Kc doesn't decrease, then you go to Riemann-Roch and so on, and you deduce that P moves in a linear system. So that's the same argument. Right? The next thing in Riemann-Roch is that if I've got two different points, then either the canonical system separates them, or the curve is hyperelliptic. So let's see whether we can do that too by the same method. Okay, so C is numerically 3 connected. Oh yes, okay. I think I better give the definition first. Okay, so I'll come back to that. So C is, this is Fabrizio Catanese, honestly hyperelliptic. If there exists a 2-to-1. If there exists a finite morphism C to P1 such that, and this morphism is called phi, called psi I think anyway, such that psi lower star of OC is rank 2 locally free sheaf. On P1. Yes. So, you know, I'm sure some of you have seen things like, you know, here I've got a curve of genus 3, which is a curve of genus 2 plus a curve of genus 1. And then I ask, what is this one canonical system? And the one canonical system could be, for example, 2-to-1 on one component, but 1-to-1 on the other component. Right? So this honestly hyperelliptic is just getting away from that by saying, you know, so this guy might have funny Kc. Right? But when I say funny, I mean it does different things to the two components. It could, for example, be 2-to-1 on. It could. I mean, this one is going to blow up this point anyway. So anyway, I'm getting away from this. So, you know, the consequence of this is that C is contained in, C is equal to C 2G plus 2, contained in weighted projective space 1, 1, G plus 1, given by, so if I call these x1, x2, W, given by W squared plus A g plus 1 x1 x2 w plus b g plus 2 2g plus 2. Right, and this is very special. So, you know, this surface here is just a little bit singular at this point. However, the curve is not allowed to pass through that point. Right, and so this means C is a curve on a non-singular surface. And it has this 2-to-1 map. And so this means, you know, if it's non-reduced, then without loss of generality, well, you know, in characteristic 0, let's not worry too much about characteristic 2, well, it's w squared equals 0. Right, so there is a possibility of a non-reduced curve here, but, you know, he's not so bad. This is just, you know, the infinity section of this scroll with multiplicity 2. So this is a, you know, comparatively nice one. This one is, you know, 2c with c squared equals, sorry, 2b with b squared equals g plus 1. Right, but otherwise, it could have two components. It could look like this. Then the world's not such a bad place. Right, so these are completely tame curves. So if C is numerically 3 connected, then either KC is very ample, or C is honestly hyperelliptic, or C has PAC equals 0 or 1. I'm not quite sure whether this case 0 actually occurs, but let me not worry about it. Okay, so we're getting results here that are exactly as good as the ordinary case of a non-singular curve. Right. Let me not give the proof here, because otherwise I'm not going to be able to finish. I don't want to spend the rest of the lecture course just talking about this one sort of basically rather technical area. So you know, there's quite a lot of other things that are fun in this paper. So I'll try and get to the main. I'll try to get to the main theorem in the second half.